doing well. I'm going to continue with this chapter and probably finish this today. Bulk of today's lecture is going to be with numerical questions. So you want to get a scientific calculator and also a periodic table. I'm just backing up to this slide. This is where we stopped. We were looking at concentrations of solutions. What that means is how much solute is there in a solvent. So that is what is referred to as concentration. So, you're going to have a minimum amount, a smaller amount, and that's the solute. In a larger amount, that's a solvent. But how much exactly? How much solute in a solvent? And that is referred to as concentration. So when we get to concentration, you can divide the solution into three kinds. That's kind of where we stopped our lecture on Tuesday. You can have a saturated solution, which is the maximum amount of solid you can dissolve. So I just took an arbitrary example where you take 100 grams of water, and then you have to define the temperature, because at higher temperatures, solubility is greater. So let's say the most you can dissolve is 25 grams, then 25 grams of solute in 100 grams of water. 100 grams of water is called a saturated solution. Anything less than 25 grams is unsaturated solution. So 25 grams is not like you have a Galton number or your molar volume. It's just a number that I made up. So I don't want you to give any significance to this number 25 grams, okay? Then we kind of talked about how we can force more than 25 grams to dissolve. Maybe you could force an extra 5 grams in the same amount of water. And to do that, we have to go to a higher temperature, and that's called a supersaturated solution. And I kind of wrapped up the lecture by saying that supersaturated solution is quite unstable. So that's where we are going to continue here. What we have are three pictures. The first one is water, which contains sodium acetate. For those who are curious, this would be the structure of sodium acetate. Acetate is a polyatomic ion. That's something that you did not memorize, okay? It's one of those ions on the table that you were using. It does completely dissolve. If you take the solubility rules, anything that has sodium ions and anything that have acetate ions is going to be completely soluble in water. And don't miss the fact that you are applying heat. So I'm going to put a little triangle. What that means is heat. And you're somehow forced more than the maximum amount of sodium acetate. So what we are looking at in the first picture is the supersaturated solution of sodium acetate, which means you go to the maximum amount of sodium acetate and then you go a little bit more after that. And so it must be on a hot plate. It must be kept hot. Now it's very unstable. That's what we're talking about. And you can prove the instability actually in a couple ways. One way is shown in the picture. You can see a tongs here, and in the tongs, there is one little crystal. This is a crystal of sodium acetate. So you could take a small crystal of sodium acetate from your manufacturer, just place it on top of the liquid, and you can see how so much of the sodium acetate comes crashing out. This is basically the excess amount of sodium acetate that you forced it to dissolve, but then what happens is pretty much a lot of it just comes crashing out, even if it is under heat. Okay, all of that will just simply come crashing out. So one way the supersaturated solution can crystallize is to add what is called a seed crystal. This is our seed crystal. If you add a seed crystal, the whole thing will come crashing out. This is a great way for making crystals in the lab. So those who will move on to study more chemistry, and hopefully you will get back to lab and do all these wonderful things. You will create always a supersaturated solution, and then you will just add a little seed crystal. Then you'll see beautiful shaped crystals grow. There's another way to do it, and that's not shown in the picture, and that is a mechanical disturbance. So how do you bring about a mechanical disturbance? It's not like you have to lift up the beaker and shake it. Yes, you can do that, but then you don't get beautiful crystals. What you do is scratch the inside walls of the beaker. So what you have to scratch it, and how do you scratch it? By using a glass rod. because we have a little bit of disadvantage of not entering the lab. This is how a glass rod will look. It'll be just a cylindrical piece of glass, and then you just take that glass rod and scratch the inside. You literally have to create scratches on the inside. So what you're doing is creating rough surface inside walls of the beaker. Now have some rough surfaces, and now what can happen is that mechanical disturbance will start the crystal formation, and the crystals will anchor on to these rough surfaces, and then they'll start growing. This is another common way in which crystallization begins in the lab, where you can form crystals. So when we look at the three solutions, saturated, unsaturated, and supersaturated, we're not really defining the exact amount of solute in the solvent. We're just saying what's the maximum amount, and that can change from substance to substance. So I could go to the lab tech and say, give me an unsaturated solution of sodium acetate or anything like that. And what the lab tech can do is basically can give me a variety of unsaturated solutions. Can be anything less than 25 grams will be unsaturated if 25 grams is saturated. If I say supersaturated, it can be anything about 25 grams. Okay, so it can be 30, 35, whatever. So you can see that, you're not being very specific when you say unsaturated, supersaturated. Saturated is perfectly fine because it's a maximum amount that has already been determined for a number of substances. As a handbook, all you do is open the handbook and it tells you what's the maximum amount of substance that can be dissolved in 100 grams of water for a variety of substances. But when you get to unsaturated and supersaturated, you don't have that kind of specificity of those terms. So we are going to look at two terms, out of which the second one is like super important, but we're still going to cover the first one. That's called the mass percent. And then, of course, we'll follow everything with some numerical problems stressing on the concept. Now, the mass percent is defined as the mass of the solute. So how much of the solute you add in the mass of the solution. So what you must remember is mass of the solution is the mass of the solute plus mass of the solvent. So solution has two components times 100, that is mass percent. So grams of solute divided by grams of solute plus grams of solvent, that's going to be mass percent. So this is something that's commonly used with agricultural products and also in the drug industry. Pharmaceuticals, usually mass percent. Let's take a look at a problem. So you want to prepare a solution using 5 grams of sodium chloride in 97 grams of water. What you should remember is the smaller amount is always the solute. The larger amount, 97 grams, is the solvent. So water is the solvent. Mass percent is going to be mass of solute, and that's going to be in grams, divided by mass of solution. So mass of solution is going to be solute. I keep stressing this because a lot of times students will think it's mass of solvent. It's not, it's mass of solution. So this is going to be times 100 because we want the percent. Mass of solute is 5 grams. Divided by mass of solution is going to be solute plus solvent, right, times 100. So go ahead and get me the percentage for this. And then you want to go with 3 significant digits because 5.00 has 3, 97.0 also has 3. You want to go with the least number of significant digits. So you will get 4.90%. Really straightforward problem. It's also another one called mass by volume percent. So that, is very similar, but it's not something we use a lot, but just for your own knowledge, mass of solute, but now it is volume of solution, but again, as I mentioned, we won't talk about this, but this is a little thing, and I rarely seen this asked. As I said, the second one, molarity is where you're going to be heavily tested on. Let's try another problem in the same concept. I'm not seeing anything in the chat session, chat window. If you have any questions, feel free to ask me as always. What mass of a 5.00 mass percent solution of dextrose contains 25 grams of dextrose? So what we have is a 5.00 mass percent. So what that means is if you got 100 grams of solution, you got 5.00 grams of dextrose. Right? Makes sense because 5 over 100 times 100 is 5.00%. So that's your unit equation. See, I'm getting back to unit analysis because that's what we will use. Now we got 25 grams of dextrose times. I always like to cancel, right? Remember, we always like to cancel what we start with. So we're going to write 5.00 grams dextrose at the bottom so that we can cancel that. And then we will have 100 grams of solution on the top. So it's a fairly straightforward. So you're going to get 500 grams solution, but that's not the correct number of significant digits. So you have 3 significant digits and 5.00. 25.0 also has 3 significant digits. So there are a couple of ways of doing this. You can just do this, or you can move this 1, 2. So you will get 5.00. Now you have 3 significant digits. You don't want to leave it as 500 though, you know, you want to be careful with the significant digits. I personally don't like this, but that doesn't mean it's wrong. I like to go with a scientific notation. I rather do it this way. Why is this equation set up? Because you can also set it up that way if you want. But this one can directly go into an algebraic equation. And if you like, you can set it up as an algebraic equation. It doesn't have to be different. I just use the unit analysis approach. You can do it one way or the other. Last time we were given both grams. This one we're given 1% and 1 gram. That's right. So you have to read the 5.00 mass percent and you have to convert it into grams. But to going back to this, you can also use the equation if that's what you guys want to do. 5.00 mass percent, and then you want to find the mass of the solute is 25 grams. What you're attempting to do is you can certainly, you know, go ahead and use an algebraic method, but I think this would work out just easier. That's it. So the next section is super important, and we have a variety of numerical setups, just like chapters 8 and 9. I have all kinds of problems here, and we are going to use the unit analysis approach to move from one unit to the other. Now, a really clear way of defining the concentration. Yes, those who are having Wi-Fi issues, if you're just having a lot of problems, just log out and you'll see my recording, because I'm having the same, like I had to cancel my classes on Monday and I just got lucky Tuesday and Wednesday. Again, didn't have internet this morning. I only got it like at 11:30 today. And I joined right away, and they're coming again to check tomorrow. So don't stress yourself out. Just log out. I will not mark you off on attendance or anything. There's a problem with Cox. If you're on Cox, there's a problem. That's all I know. So go ahead and have a good day, and I will get this posted right away, okay? So the really accurate way, or the way that chemists like to use, is to say exactly how many moles of the solute is there in the solution. And this is expressed as moles per liter. So MOL divided by liter, and that is defined as molarity. So molarity is defined as a number of moles of solute dissolved in solution, but keep in mind the solution must be expressed in liters. So molarity is defined as a number of moles of solute that is dissolved in the solution, but the most important thing is the solution must be expressed in liters. So we're going to start off by calculating molarity. What is the molarity of a solution containing 24 grams of sodium hydroxide and 0.100 liters of solution? Now, there are a couple of ways of doing it. I leave it for you. You can just substitute it in this formula. But if you're moving any further with chemistry, they won't like that method. Instructors don't like that method. So I'm going to use the unit analysis approach. But I will use the other method for students who are just interested in that, okay? Just for one problem. Now, the most important thing you want to realize is you're going to calculate molarity. Molarity is represented by big cap M. That is the letter used to represent molarity. And the unit is molarity. Molarity is the name of a unit. But if you break it down any further, it's going to be moles over liter. So our final answer should be something moles on the top, liter on the bottom. That's what I want to stress about, okay? So we can, so what I'm saying is you should never have 0.100 liter on the numerator because the liter is on the denominator. That's the key thing. So you have two pieces of information, 24.0 grams and 0.100 liter. You cannot start with this, okay? You cannot strike through the liter because you really need the liter on the denominator. You just cannot strike through the liter. Now I'm going to start with 24.0 grams because I don't want grams. What I want is moles of sodium hydroxide. All right. So this is 24.0 grams of sodium hydroxide. I want moles on the top. So I want you to find out what is the weight of 1 mole of sodium hydroxide, which means you're going to get the molar mass of sodium hydroxide. So we need the periodic table for this. So we will go here and take a look at sodium hydroxide. So I wouldn't spend, as I said, we will only go to the first two decimals, and then this should be 15.99, and then this should be 1.00. So go ahead and get the molar mass of sodium hydroxide. I'm just adding up, but this time you should be pros in this. I'm just adding up the atomic weights, and that gives you 39.97. You don't even, if you had it as 40, you'll be totally okay. That's what I'm trying to say. So now we have 39.97 grams of sodium hydroxide. I don't care if the grams get canceled because you see in the final unit, I don't have grams, I have moles. Now what you want to do is you don't have anything on the top, so you can put 1. And then at the bottom, you want to have 100 liter. Now what will happen is your answer will be in moles per liter, which is the same as molarity. So go ahead and complete this calculation, which is going to be a fairly straightforward one for you guys compared to everything else you have done in the previous chapters. So you should get to 3 significant digits. So 6.00 moles per liter. Moles per liter is written as capital M. Capital M, big cap M means moles per liter. This stands for molarity. This is using the unit analysis method. So I'm okay if you use the other method, but most instructors will not be. So you could use this formula here, equal to moles of solute. So moles of solute, you have to actually calculate. That's going to be 24.0 grams divided by 39.97 grams divided by liters, which is 0.100 liters, okay? So you must actually calculate the moles. That is 24 grams times 1 mole divided by this, which is very similar to the setup I have, and you'll get 6.100 M. So this would be using an algebraic method where you'll have the moles of solute and then the volume in liters. If you want to use that method, you can. But my focus is more on unit analysis because that's what they want you to know especially students who go to engineering, unit analysis is called dimensional analysis and takes, great significance in those. And Gen Chem, you'll use unit analysis. Okay, any questions on this one? Okay, let's go ahead and try one more together, and then I'll give you some time to work through a few of these. So we're going to start with the first one. This is problem 54, 1 gram of KCl in 75 mils of the solution. So you do not want to start with 75 milliliters because you don't want to cancel out the milliliters. Keep in mind, your liters have to be on the bottom. This is milliliters. We will convert it into liters, but you really want to start with this. KCl times, you want to have 1 mole KCl on the top. Bottom, you want to get molar mass of KCl. So we're back to our periodic table. Potassium should be 39.09, and that should be 35.45. So go ahead and get the molar mass of KCl. This is potassium, this is chlorine. Right, so you get 74.54 grams per mole. That is your molar mass. So I'm going to transfer that here. And then I'm going to cancel out grams of KCl. Now I want liters. So top, I'm not going to have anything. You just have 1. Now this is 75.0 milliliters. Make sure you convert it into liters. So 1000 milliliters equals 1 liter. You want to cancel out the milliliters. So you want to have that on the top, liters on the bottom. So now you see milliliters get canceled. At the end of all this, your answer will be moles over liter, which is the same as molarity. So we will go to 3 significant digits. So that'll be 179 moles per liter. You can also write it as 0.179 m. Typically, although it is moles per liter, molarity is represented by the symbol m. Moles per liter and molarity, both are units. They mean exactly the same thing. So I like you to just practice, C. Just practice C, and then we will move on to another type of problem. This is going to be magnesium bromide, so I'll hold on like about 5 minutes or so. No difference between the previous 2 problems. It's just practice time. So go ahead and try this. Any questions, please unmute and talk to me, or you can text. You can put it in the chat window. So if you have it in milliliters, you have to convert it into liters. If you don't like to set it up like that, your other option is to do it this way. 250.0 times 10 power minus 3 liters. You can always do that. If you like to do that, that is totally okay. Like this section can be written like this. So you want to go again to 3 significant digits. 20.0 has 3. 250.0 has 4 significant digits. Correct answer 435. Correct. M. So instead of this entire setup, the bar, you can just go 20 times 1 over 184.1, right? And then here you can have 250.0 times 10 power minus 3 liters. Should be minus 3. Okay, hopefully you can see the minus. Otherwise, you can set up the unit analysis the way I have. So here are some extra problems that you can try. These are all from Carvin. Okay, but I think we've done 3 and you have got a little bit of idea on how to calculate molarity. So another minute here. Let me know if you have any questions. And then we're going to go to a different type of problem, yet deals with molarity. So I want to cover all the types here, just like we did in 8 and 9. That's it. So anything for me in this type of problem? Anything you want me to explain better? Anything unclear?
Can you just scroll up really fast? I want to like write a blank equation with just the information.
Where do you want me to scroll to?
That's right there.
Oh, right there. Okay. So on a side note, there are no trick questions here. You'll be asked to calculate molarity, and that's a direct question, and that's how you're going to get it. Okay, you will not see any other tricks here. Is everything good? Everyone okay? Is the second equation setup always going to be yes, because the unit liters have to be on the bottom. So it'll always have to be 1 over. You don't have anything to write on the top, so you will write 1. It'll always be like that. Wouldn't K round? I'm not round. K. Are you talking about potassium? No, I didn't round that off. If you're talking about potassium, yeah, I didn't round it off. It doesn't matter. Like I said, if you had this as 75, you still be very close to the answer. You'll be fine. No, that's no need to round off. You can go to the second decimal place and not round off. Like if you had this as 80, you still be okay, but I just didn't round anything off. Typically, you will hear this instruction from all instructors to go to the second decimal place, no rounding off. That's what we do in 130. And if you're not told that and someone didn't follow that, you still be okay, like I said. Okay, let's just stay in molarity, but look at another problem. Let's read this because let's go ahead and read this. Now I'll tell you how you need to think. How many grams of potassium dichromate? So what is asked is grams. You're given 2 pieces of data, 250 milliliters. So you're given volume, 0.110. And the way you read this is molar. You don't read it as 0.100 molarity, but instead you read it as 0.100 molar. This is potassium dichromate. Whether you know the name or not is not important. But after you complete the calculation, your final answer should be in grams. So what that tells me is this. I somehow have to get the milliliters cancel. Now in molarity, so that's why it helps to remember like this. It's actually moles over liter. I somehow have to get the liters canceled. I even need to get the moles canceled. I somehow need to get milliliters, liters, and moles canceled. And my final answer should be in grams, okay? So let's get started here. What we want to do is first understand what 0.100 molar means. What that means is you got 0.100 moles of potassium dichromate in 1 liter of the solution. Why is that? Because M is moles over liter. It's the same thing. So what I've done here is a very simple thing. I've just replaced the moles, that capital, the big cap M, with this, moles over liter. That's all I've done. Okay, so this is what we are going to do here. We can start either with 250 milliliters or 0.100 M. It doesn't matter, okay? So let's say I'm starting with 250 milliliters, 250.0 milliliters. Keep in mind, you need to convert it in liters. You cannot cancel milliliters and liters, all right? So this is going to be 1,000 milliliter. Top is going to be 1 liter. In that way, what happens is the milliliters get canceled. You have liters. Remember, we don't want liters either. We want to cancel that too, right? So times, you still got another piece of data used. We have already used this. I decided to start with that. You don't have to. You can start with 0.100. Now, I want to cancel the liters as well. So what I need to do is have 1 liter on the top, 0.100 mole on the top, and 1 liter on the bottom. That's what I meant. You know what I meant, right? So liter and liter get canceled. I don't want moles either because I want my final answer in grams. So what you want to do is 1 mole of potassium dichromate, you want to get the molar mass of that. So we are going to get the molar mass of potassium dichromate. Before I actually do that calculation, I want to repeat this. I decided to start with 250.0 mils. I'll also do a setup by starting with 0.100 mils. So you don't have to worry about which one to start with. You write 250 milliliters. You have to convert it into liters, and that's what we are doing here. So milliliters becomes liters. You cannot cancel milliliters and liters. You can only cancel liters and liters. Now this one is nothing but 0.100 M. I've just expressed the M as moles over liter, but I wrote it in such a way that 0.100 mole is on the top and the liter is on the bottom. Now my goal is to cancel the moles. So 1 mole of potassium dichromate is going to be equal to the molar mass. So I want to calculate the molar mass. So let's go to the periodic table and start there. So potassium is going to be 2 times 39.09. I'm not rounding off. You can see, no need to worry about it. Chromium is 51.99. Oxygen is 15.99. And if you wrote it as 16, it will be all good. So get the molar mass of this and the sum of that. Please do this calculation because in one way, you check what I'm doing as well. So I'm getting 294.09 grams per mole. So this is the molar mass of this compound called potassium dichromate. Whether you know the name or not is not important, but the formula is necessary and it's already given to you. Now this you will write on the top. So that's 294.09. See how you've canceled everything and your final answer is going to be in grams? Now 0.100 has 3 significant digits, 250.0 has 4 significant digits. Your final answer should have the least number of significant digits, so it should have 3. So go ahead and complete the calculation. We want 3 significant digits. Let me know you guys getting this. Excellent. So now this was starting with 250 milliliters. All right. We could have started this with 0.100 M, and that's what I want to do in my next problem. So you don't have to memorize, oh, for this kind of problem, I have to start with 250. No, you start with You have two pieces of data given. You can start with one or the other. We started with the volume. Next time we will do the opposite. We'll start with the molarity. Before I do that, any questions on this one? So unit analysis is moving from one unit to the one that is actually asked. So what is the mass of the solute in each of the following solutions? I'm just taking this first problem here. That's what I have there. So let's go ahead and see. This time, I don't want to start with the volume. See, I started with the volume, 250 milliliters. I don't want to start with 1 liter. I'm going to start with the molarity. So 100 M, but I'm not going to write M, but M is moles over liter. I'm going to write it as moles over 1 liter. Moles over liter means per liter. That is moles per liter, right? That's how you read it in math. That means it's over 1 liter. Keep in mind, we have to cancel out the moles. We have to cancel out the liters as well, all right? So now we need to, let's cancel out the liters and look at the volume. You actually land up using both pieces of data. Which one goes first is your choice. I want to cancel out liters. So what I'm going to do is write 1.00 liter on the top. All right, so bottom, you just write 1. You don't have anything there. So what's happening now is you cancel out the liters. Now I want to cancel out the moles. So the bottom, you write 1 mole of sodium hydroxide. So what happens is now the moles get canceled. How much does 1 mole of sodium hydroxide weigh? It's 39.97 grams. See how you get the answer now in grams. So you want to go to 3 significant digits, right? 3 point, yeah, 4.00. Because you're getting 3.997, right? Grams. So you want to go to 3 significant digits. That'll be 4.00 grams. So that'll be your answer. Okay, I want you to try one on your own now. That's going to be C. So go ahead and try C. I'm not seeing any questions in the chat window. Anything, please let me know. But I want you to try this on your own now. It's your choice. Either you can start with 25 mils, but remember to convert the milliliters to liters, or you can start with 0.500 M molar. It's up to you. So you could use the previous methodology or the one for this problem we just completed. Choice is yours. So if you're not getting 1.68 or you want me to explain something here, let me know, but I'm going to wait for you to finish your work here. Some of you might have started with 0.500 moles, and that is also okay. I'll go ahead and show the setup for that on the other side here. Oh, 25 milliliters. I'm sorry. So you can see this approach here. Instead of writing 25 milliliters, I want to cancel the liters. So 25 divided by 1,000. What I have done there is to write it as 25 times 10 power minus 3 liters. So it's the same thing. 25 milliliters can also be written as 25.0 times 10 power minus 3 liters. So you can certainly use that kind of conversion as well. Any questions with this problem? Okay, we're going to stay in molarity, but we're going to look at another variation. What volume of 12 molar? This one is going to be read as molar. HCl contains 9.15 grams of HCl. This can be a little misleading. This is actually molar mass. Carbon uses big cap M for molarity as well as molar mass. This is actually molar mass because you can see the unit there, grams per mole. Okay, so we want, what is it that we are asked is you're asked volume. Okay, so we want the final answer either in liters or milliliters. That's up to you. As I said, the easiest would be in liters, but if you need to convert it into milliliters, you can certainly do that. Now I'm going to take this 12.0 mole and molar solution, and I'm going to read it as 12.0 moles of HCl in 1 liter of the solution. It's the same as that because molarity is moles per liter. Okay, so we don't want the liter on the bottom because we want the answer as liters, right? So we don't want the liter on the bottom. We want it on the top. So that's something you want to keep in mind. Or in other words, you want moles on the bottom, liter on the top, which means you want 12 molar on the denominator. Okay, you have to get it positioned in such a way. We definitely want to cancel out 9.15 grams. Okay, that's an important thing we want to keep in mind. So let's get started with 9.15 grams. The reason I like to start with that is I want to get the molarity on the bottom. In that way, I'll get the moles on the bottom, the liter will go on the top. Now I want to cancel this. So I'm going to have, see if you don't copy anything yet here. If you have moles here and you have 36.46 grams here, what happens is as you set it up, you can see the moles is on the top. Okay, I really want the moles on the bottom, the liter on the top. Okay, so what you want to do is this. You want to go opposite here. So you really want to go with 36.46 grams. You can see how I'm inverting it over 1 mole, right? Then 1 divided by 9.15 grams. So what you're doing now is canceling out the grams. Moles is on the bottom, which is good. And eventually we want to cancel out the moles as well, right? We don't want moles. We want liters. Now what we're going to do is we're going to have molarity on the bottom, which means 12 moles, 12.0 M is on the bottom. So what will happen now is you will get 1 liter, and then your 12 moles will be on the top. Oops. So now what happens is your moles is getting canceled. Your liter will be on the bottom, and you really want to have the liter on the top. So we have to start setting it up differently. So this is going to be 12 molar, which is 12 moles over liter. You want to invert that. So what you want to do is 1 over 12.0 liter over mole. So set it up like that. Then 1 mole on the top so that you can cancel out the mole, right? And then you want to have your 36.46 grams on the bottom, and then 9.15 grams on the top. So now you'll see everything getting canceled the way you want. That's 12 moles per liter. So here you can just write it as moles, and moles will get canceled. So this is how we start, sorry. And then your grams and grams get canceled. Your answer will be in liters. So go ahead and finish up the calculation, and then we'll do another problem of the same kind. So volume should be in liters. If you get that, it'll be a really small number. You want to go to 3 significant digits. So 209. Those who don't like this and would like to convert it into milliliters will times it by 1,000. So that'll come out to be 20.9 milliliters. So when you set it up, you want to be careful. In my first setup, the liters comes on the bottom, and you don't want that. You want the liters on the top. So all you're doing is inverting this. So typically molarity is moles over liter, but you can invert it because the unit equation will be 1 liter equals 12 moles. Which one goes on the top, which one goes on the bottom doesn't matter because you have 2 unit factors, 1 liter by 12.0 moles, and your other unit factor is 12.0 moles over 1 liter. Okay, so you want to use the appropriate one. So you want to go with this setup, all right? And then you want to cancel the moles. So moles on the top, grams on the bottom, and you want the grams to get canceled. So 9.15 grams goes on the top. Now, as I mentioned, we can either start with 12.0 molar or we can start with 9.15 grams. You can go one way or the other. But before I go to that, any questions with this setup? I do want to do another one, and then I'll give you a chance to do one, okay? Okay, let's try another one because I'm not seeing anything in the chat window. So let's start with this one. 2.50 grams of the solute in 0.325 molar. So what we can do now is this time for a change, we will start with 2.50 grams. We do want to cancel out the grams. So on the top is going to be 1 mole KNO3. We'll have to calculate NO3, and that's going to be 39.09. Let's say nitrogen is 14, oxygen is 3 times 15.99. As I said, if you wrote it as 16, it'd still be good. So let's go ahead and get this. This would be the molar mass. So I'm getting this as 101.06. I'm going to write 101.06 grams. So my goal is first to cancel out the grams. So I got moles on the top, so I want to cancel out the moles. So let's look at what we have here. This is 0.325 molar. What that means is 0.325 moles in 1 liter. So what I want to do is I want to have 1 liter on the top. I want to have 0.325 mole on the bottom, right? Makes sense because this way what you can do is cancel out the moles and your answer will be in liters. So this time I started with grams. So I'm getting to 3 significant digits. And those who like to convert it into milliliters can multiply by 1,000. So that'll be 3 significant digits, milliliters. So I'd like you to take a moment and maybe just do B. So that you could either start with 2.50 grams or you can start with 0.325 grams, but this is a different compound. This is aluminum bromide. So you have to get, yeah, liters or milliliters. If it's multiple choice, you see which one is given. But if it's not multiple choice, it's free response. You can submit the answer in liters or milliliters. I don't think this question is asking a particular unit. Yeah, you can leave it in liters, Carly, and that'll be fine, or milliliters. The question is specific about which unit. It's usually liters or milliliters. If it's specific, then you have to do this conversion to get to milliliters. Otherwise, you can leave the answer in liters. It's multiple choice. You're not going to see both these answers. You're not going to see liters and milliliters as your choices. You'll see one or the other. Now, some of you may desire to start with 2.50 grams, and some of you may desire to start with 0.325 molar AlBr3. So, but everyone should calculate molar mass of aluminum bromide. So bromine is 79.90. Aluminum should be something like 26. I need to check. Yeah, 26.98. So you do want to get the molar mass. A lot of times it's even given to you because that's not the goal of the problem. So a lot of times molar masses are given to you. That's the molar mass. If you're getting something different, let me know. I'll run my calculation again. So this time, I'm going to start from molarity. You do whatever you're doing, but this is what I'm going to do. This is the same as saying you got so many moles in 1 liter. I want liter on the top. I want my moles on the bottom. Because my answer is volume. So I want my answer in liters or milliliters. But I got to have the volume unit on the top. You want to start with 2.50, go ahead and do it. Nothing wrong with it. You don't have to do exactly what I'm doing here. Now, whether you want to write this one or not is optional. You don't have to. Yeah, you have the right answer. Good. We're going to go to 3 significant digits. So wait for a couple more minutes for everyone to wrap up. If you have any questions, let me know. So, while you're doing that, I just want to summarize the 3 types of problems we have learned. You can be asked to calculate molarity. You can be asked to calculate number of grams of solute. So you can be asked to calculate molarity of a solution, number of grams of solute. You can be asked to calculate volume of solution. This one, of course, you have a choice of unit. It can be milliliters or liters, or if you're specifically told one, you just stick with that. This one, you're going to come up with a unit M, and this one, of course, is going to be grams. So these are the 3 types of problems that we've completed. Any questions with the aluminum bromide setup or the problem? So let's move on to our next question. Next kind of problem here. We're still staying in molarity. This will be the last type of problem. So this is what our lab techs will do now. I won't tell him, give me a saturated, unsaturated, or supersaturated solution. I'll specifically tell him what the molarity is. I'll tell him, give me a 0.543 molar solution of sulfuric acid. This is how specific I'll be. Now, he'll go to his stockroom and he will not find 0.543 molar sulfuric acid. Instead, what he's going to find is an 18 molar sulfuric acid. This is what manufacturers sell, and this is concentrated sulfuric acid. So there's no way in any laboratory we can purchase and store a variety of molarities. So what we do is we buy the most concentrated form of that compound available, especially if it's an acid or something, because it's difficult to store acids. They're corrosive. We'll keep it. So what we need to know is this is a concentrated solution. What I'm asking him is a much more dilute solution. So I need to add water to this and bring down the molarity from 18 to 0.543 molars. Okay. So how do we do this? What you need to do is take a volume of this, add a whole bunch of water. So this will be volume plus H2O. So what you'll be doing is adding water. So you're going to have a more dilute solution. So you're just going to add a whole lot of water. You're just going to take a little bit of V1, which is 18 molar, add a whole lot of water, and then you will get V1 plus H2O. And that's how we're going to dilute it. The equation we're going to use is M1V1 equals M2V2. So let's see what that means. Want to make sense of that? So we're going to start with a concentrated solution whose molarity I know is 18 molar. Okay. Whose volume that I'm going to take is V1. I'm going to take some volume. Then I'm going to end up with a dilute solution. The molarity of the dilute solution is M2 and the volume is V2. Now, M1V1 could be dilute, M2V2 could be concentrated. The left side could be right side and vice versa. It doesn't matter. But one side is concentrated, the other side is dilute. Now, the lab tech, of course, is going to ask me, how much of 0.4543 molar of sulfuric acid do you need for your 130 lab? And I'm going to tell him I need 50 milliliters. So this is what is happening. He goes into a stockroom and finds out that the concentrated sulfuric acid is 18 molar. He knows he has to make me a solution whose molarity should be 0.543, but he also knows that he should make me a 50 milliliter solution. Now the question is, how much of this should he take to get me that? This is just algebra. You'll divide both sides by 18, so you can cancel it. You remember this algebra? You divide both sides by 18 molar. That way you can cancel out the 18 molar and your answer will be V1. He will know then how much of the concentrated solution he needs to take in order to give me what I want. What I want is 0.543 concentration. sulfuric acid, I only want 50 milliliters. So let's go ahead and put this in the calculator, which is 0.543 times 50 divided by 18. Now here what's happening is the molarities get canceled. The answer will be in milliliters. You do not have to convert it into liters. We are going to go with two significant digits. He needs to take 1.5. Actually, 50 has only one significant digit, but let's leave this at 1.5. 1.5 milliliters. So he knows that he has to go to the stockroom, take 1.5 mils of the concentrated acid. So in order to obtain 50 milliliters, remember he has to add 48.5 milliliters of water to it. So he'll actually take a special flask. These special flasks are called volumetric flasks. So there'll be special ones which are graduated to 50 milliliters. So what he will do is add 1.5 milliliters of concentrated sulfuric acid. And he won't even measure the remaining, 48.5 mils. There'll be a graduation that says if you keep adding water to hit that line, you get 50 milliliters. So he'll keep adding water till he hits that line on the flask. And now he's got 50 milliliters of 0.543. So this is exactly how concentrated solutions are diluted. You don't make dilute solutions concentrated. It doesn't work. Concentrated to dilute is what this is used for. Okay. So let's try a couple problems. Fairly straightforward as long as we understand the concept. Okay, so let's look at this. What volume of 6 molar sodium hydroxide needs to be diluted to prepare 5 liters of 0.10 molar sodium hydroxide? So I'm going to make one side concentrated. That can be your left or right. It doesn't matter that the side is dilute. I'm going to say this is M1, V1. This is M2, V2 equals. My concentrated molarity is 6.0 M. What is the volume? So you're asked what V1 is. How much of this should I take to make 5 liters? But it's a lot less concentrated. This solution is only 0.10 M. So what you're going to do is either side, you're going to divide by 6M. If you do that, you'll cancel that. You'll cancel the molarity. Answer will be in liters. You saw how the previous problem, the answer was in milliliters. This time it's in liters. You don't even have to convert anything. The units take care of themselves very nicely here. So answer is we want to go to two significant digits based on 6.0. So this is exactly different solutions are prepared. So commercial sodium hydroxide that you can purchase will be 6 molar. So typically the really concentrated solutions are what we will buy. It's easier to store that and add as much water as we want to get to whatever liters we want. So in the lab, they have something starting from 1 milliliter to almost like 50 liters flasks, huge flasks. If you go to the back side, which we never go, right? Students hardly go to that side. There'll be a 5-liter flask. So you would just take 0.383 liters of sodium hydroxide, add to it. Again, there'll be a graduation. And if you like a little line etched on that flask, and you keep adding water till you get to that. A lot of times a stir bar is added, so everything is mixed really well. Otherwise, what happens is you have your acid and all your water sits on the top because of a density difference. You put a stir bar and then you turn on an instrument. What it does is the bar just rotates inside the flask and mixes everything up. Okay, let me try another problem with you and I'll give the last one for you to work through. Okay. Concentrated hydrochloric acid is 12 molar. So one side I'm going to say is concentrated. You don't have to write it. You can just remember it. I do a lot of things for teaching purposes. The other side is dilute. I'm going to say, as I said, concentrated can be M2V2. It doesn't matter. There's no definition that ones belong to concentrated and twos belong to diluted. It can be opposite. Doesn't matter. Concentrated hydrochloric acid M1 is 12 molar. What is the molarity of the hydrochloric acid solution prepared? Which means you're asked what is M2? By diluting 10 milliliters of the concentrated acid, which means you're taking 10 milliliters of concentrated acid, you're diluting it, you're adding water to get 250 milliliters of the total volume of the diluted acid. So you should be able to read this correctly. On both sides, you're going to divide by 250 milliliters. If you put the numbers on the wrong side, you will not get the answer. So milliliters will get canceled. 250 milliliters almost entirely, right, gets canceled. Your answer M2 will be in molarity. So go ahead and calculate that. So you should get 0.48. So we have two significant digits in 12. So we'll stick with 0.48. So what that means is the molarity, the concentration of the diluted solution is 0.48. I think it all comes to reading the problem correctly. I think the math itself is fairly straightforward for you guys. You've done a lot more difficult setups in your math classes. Take a moment here and do this problem. If you have any questions, of course, more than welcome to ask me. If anything needs to be explained again, please let me know. So just for the heck of it, I'm switching the sides. I'm going to say my dilute is M1V1, concentrated is M2V2. So please take a look at your setup, making sure you and I have the same thing. See, my dilute now is on my left side. It could have been on your right side. It doesn't matter. You're asked to find the molarity of the diluted solution. How much do you need to make 500 milliliters? You want to take 50 milliliters of the concentrated solution, right? And the concentrated solution is clearly told that it is 17 molar. Both sides you have to divide by 500 milliliters. That way you can, this side is just M1. Milliliters get canceled. Your answer will be in molarity. 1.7. So you're starting with 17 molar. Your dilute solution's concentration is going to be 1.7 molar. So maybe for a lab, I need 500 milliliters of 1.7 molar, and that's what I'll tell him. He'll know how to dilute it. So this is an equation that's used a lot in the lab, because this is how you move from one concentration to the other. So 4 types of problems. You could be asked molarity of the solution, number of grams of solute, volume of the solution, and the last part is dilution of solutions. In dilution of solutions, be prepared. You can be asked molarity and volume of the concentrated solution, one or the other. You can also be asked molarity or the volume of the dilute solution. So you have 4 parameters, M1, V1, M2, V2. You can be asked any one of the 4. Obviously, you should be given 3 out of the 4, right? You'll be given 3 out of the 4, asked for the missing 1. I think you can handle that algebra really well. I think you're doing well on that, okay? So you have 4 variables, M1, M2, V1, V2. You'll be given 3. You calculate the missing 1. So I'm going to take a look. I don't remember what I have in Canvas. I don't know if I have extra problems. If not, I'm going to post some extra problems. They are there in Corvin, but I like to post some extra ones. And one thing I want to do, which I haven't done, is I'll do a recording of all these different types of problems. And I'll post some pencast recordings as well, in addition to what I have taught you here. With that, I think you'll nail down these 4 types and add it to your list of numerical problems that you've learned this semester. So when you come back Tuesday, we're going to go back. We're going to look at solids and liquids. Okay, that's what we will do. And then we'll start winding down for the semester. Okay, so I'll make sure you get extra problems, Samantha, and I think everyone will be happy to get back to face-to-face classes in fall, but we'll wrap this up. One of my goals is to make sure that you guys get through, which means you will turn in everything promptly. If not, email me. I expect some delays in things getting turned in because Cox has been totally screwy. So please do keep me posted, and I'll get back to you. Okay. With this, we will stop. If you have any questions, you can stay back. Otherwise, we call it today, and then we will meet Tuesday. I will hold office hours. Okay, that's it from my side. Thank you. I am seeing some things. Chem 101 assignments. There'll be one due on, not on Tuesday, not on Thursday. There'll be one due in solutions, but it'll be mostly Sunday night, next Sunday night, not this Sunday night. I'm hoping that'll give everyone some time for the internet to get settled. Okay. So private messages, I'm going to answer them privately just after stopping to share. But if you have any questions, please stay back. I'll stop the recording.